worried about the kids, homie. Lisa's becoming very obsessive. This morning, I caught her trying to dissect her own raincoat.
I know. And this perpetual motion machine she made today is a joke. It just keeps going faster and faster.
And Bart isn't doing very well either. He needs boundaries and structure. There's something about flying a kite at night that's so unwholesome.
Hello, Mother dear.
Oh, that's it. We have to get them back to school.
I'm with you, Marge. Lisa, get in here. In this house, we obey the laws of thermodynamics.
Okay, so laws of thermodynamics. We're going to start by talking about entropy. And you may wonder, what does entropy have to do with this class? It's not a physics class, but we are dealing with information. And turns out that the field of information theory, which began by a very important paper in 1948, deals with this notion of entropy. So Claude Shannon is the founder of information theory. And in fact, information theory is my field of research. We're just barely going to touch on it a little bit today. So has anyone heard of Claude Shannon or information theory? You've heard of one or the other. You've heard of Shannon. Okay. He was at Bell Labs at the time, and this work really has had a huge impact. For example, the word bit first appeared in Shannon's papers. So we use it all the time. Now we're used to bits being binary digits, but there was no notion of a bit before this. And so let's talk about what was the context that they started talking about bits. Okay, maybe a little bit surprising to you. And it has to do with random variables and trying to quantify how random they are. And think of that as how much information is contained in a random object. All right, so we can define this quantity. We use h to be the entropy of x, where x is something random. And entropy is actually a feature of the distribution of x. So if x was, in fact, not very random, maybe it's not random at all, it's a particular value, and we know what it is, then it has no entropy. But if it's random and can take on many different values, and we're not sure which one it's going to take, then it actually has some entropy. And in fact, mathematically, it's just defined the following way. It's an expected value. Recall that we've defined what an expected value is, of the log of 1 over the probability mass for that value of x. Now let's try to conceptualize what this means, because it's a little bit weird in terms of expected values. We have the probability mass function inside the expected value. So that's maybe a little bit unusual, but if we write out what this is, an expected value is just a sum over all values that x can take of the probability of that value times this function. And this function was log of 1 over that same probability. So we see that probability mass function appears twice in this sum. Okay? Usually in expected values it just appears once, but here it's appearing twice. All right. Now, notice I'm specifying log base 2. In fact, you can choose any log you want. You'll just get different units for this entropy. If you do log 2, then we call the units bits. And that's where that word bits comes from. It's the entropy using log base 2. Now, the way it was described is that 1 bit is the amount of randomness in 2 equally likely events. So let's look at that example. This will be our first example of a random variable. It's just an unbiased coin flip. So x is either 0 or 1, heads or tails, 0 with probability a half, and 1 with probability a half. There's your unbiased coin flip. Now, of course, that means, another way to say this is that the probability mass function for x equals a half for both those two values. If x is either 0 or 1, it's a half, and it has no probability of being anywhere else. Okay, so there's the probability mass function for that unbiased coin flip. And we can then calculate out h of x equals, now we'll just go through that sum. There's only two possible values, so we get 1/2 log of 1 over 1/2 plus the same thing, okay, because the probabilities are the same for those two. So this is what we get, and you can see that that equals log 2, which equals 1 bit. Okay, so indeed, the 1 bit is the amount of entropy between two equally likely things. Now, what if more generally we have, let's say, a binary random variable, but it's not equally likely? Well, then we get less entropy, less than 1 bit. So that would be example 2. Let's just say that the probability mass function has two values, p and 1 minus p. So it's with probability p, x equals 1, with probability 1 minus p, x equals 0. I guess I should have a third entry here that says there's no probability of anything else. Okay, so this is just a general biased coin flip. And here we can write out the formula that the entropy is going to be p log 1 over p plus 1 minus p log 1 over 1 minus p. This comes up so often, people sometimes give this formula, it's a function of one variable, p. They give it a name, they call it the binary entropy function. All right? But let's just plot it. We see that there's symmetry in this function. So if p is the parameter, is the bias of your coin, and we say how much entropy does it have? Well, the bias can only go between 0 and 1. And we get that something like this. And it peaks out at 1 bit. Should be symmetric. I know I didn't draw it very nicely. 1 bit. Should I try that again? No. All right. I'll move my 1. Okay, so here's the binary entropy function. And you notice, of course, it's symmetric in p because, you know, one thing to notice about entropy is the actual values that x takes doesn't matter. Only their probabilities matter, because this formula here for entropy, the only way that x shows up in this formula is this function, this probability, right? So in fact, if you instead said that x equals 0 or 1,000 with probability p and q, it doesn't matter what values x takes. It just matters their probability. So entropy only depends on the probabilities themselves, not the values of x. Now, as we get into, we'll go through some more examples of entropy, but it may seem kind of weird, first of all, why this name entropy is an entropy of physics concept. Well, actually, von Neumann suggested the name to Shannon. When Shannon discovered these discoveries about information and this formula came up, von Neumann said, oh, that's like the formulas for quantum mechanic entropy, so the name stuck. All right. In fact, there's a very strong connection between the two. But it turns out that entropy answers almost all fundamental questions about compression and communication and dealing with noise. So it's pretty surprising that such a simple, nice formula gives so many answers. The answers to, we're not going to get into those theorems and that side of the real information theory in this class, but we will see that it's related to compression. We'll see at least that much. Okay. So let's see. Let's do another thing. Suppose that x can take on values in some set omega, right? And they're equally likely. Okay, this would be the uniform distribution on some set omega. All right, let's call that the uniform distribution. And So we could write the probability mass function. By the way, notice a few subscripts I might leave out. I sometimes leave out the x for the probability mass function of x, because since I'm putting x in both places, it seems a little redundant. So forgive me if I leave out this subscript x. Secondly, I might leave out the 2 on log. I'm always doing log space 2, but all of these equations hold if you just choose your favorite log. You could do natural log everywhere. It just wouldn't be bits we're talking about. If you use natural log, people say those are nats instead of bits. All right, we're not going to care about that. So what it means is that the probability of everything's equal. Since they have to sum to 1, then that means that any individual item has probably 1 over the size of the set. Okay. So what's the entropy of this type of thing? So the entropy here would be, again, it's the expected value of the log of 1 over p of x. That's supposed to be a capital X in there. All right. And this, of course, is going to be, now we know that p of x was just constant everywhere. It's just expected value of log of 1 over the alphabet size, or the size of omega. Okay? And that's no longer random, so expected value does not matter. We can just drop the expected value once we have something that's not random. So it's log 2 of the size of omega is the entropy. All right? So for uniform distributions, the entropy is just log of the size. Turns out that uniform is if you're dealing with distributions on a fixed set, uniform has the most entropy. Okay, any other distribution will have less entropy than this. So this is an upper bound on the entropy, based only on the size of the set. Okay, and that kind of makes sense. You would think a uniform distribution is sort of the most random. So if you want to just think of this for now as like an intuitive idea of how random your random variable is. Imagine if your random variable, let's say it could take on 20 different values, your random object, but one of them happens 99% of the time, and all the rest happens, some are divided up the last 1% of the probability. Well, you would expect this not to have, it's not really that random. You pretty much know what it's going to be. And also you would find that the entropy is very small in that case. Okay, so it kind of matches our intuition for how random something is. It has other nice properties, and you could argue that it's an interesting quantity just based on its properties, and there are books written about that, about why entropy uniquely has all these nice properties of randomness and information. But we won't go into that here. Let's look at a few more numeric examples of entropy, and then we'll see how it connects to data compression. Because really, the reason to care about entropy is because of the actual questions that it's the solution to. Right? So. But let's practice a little more. Entropy of a roll of a die. Okay, so a die has 6 sides. They're equally likely. So it's a uniform distribution. Therefore, we just calculate entropy of uniform distributions as log of the number of possible outcomes. That's 2.58 bits. There's the entropy of a roll of a die. Okay. Now, what if you have 2 rolls of a die? So you roll 2 dice. We want to know their pair of outcomes. All right, so in other words, we'll say x1 is a random variable. That's the first die. And x2 is the second die. Well, first of all, we're going to make a sort of obvious assumption that the 2 dice are independent of each other. Okay, so you might record the outcomes of the dice in a pair like this. And so you'd say, okay, they get some. You roll it and you get some value. For example, maybe you happen to get 1, 5. Okay. Well, the probability of any pair. So independence, we haven't talked about random variables being independent, so let this be the first time. Independence means that the probability that you get one outcome, like let's say x3 equals 1 and x2 equals 6, Independence means that this probability is just the product of the individual probabilities. So that's general. That's a general definition of two random variables being independent, is that the probability of one of them being in some set and the other one being in some other set is just the product of their individual probabilities. Okay. So this is very natural. I mean, without studying probability, you've played games with dice and you've all done this calculation, right? And you know that the probability of any individual pair is just going to then be 1 over 36. Okay, so in general, for this problem, we have that P of any A and B, P of getting a pair, is probability that x1 equals A and x2 equals B. Let's define that. I guess what I'm saying here is let us define now a joint probability mass function that has two numbers rather than one. And that means the probability that you get A and B is defined as given here. Then we know that the probability that of any two numbers for this dice roll is 1/6 times 1/6 because they're independent equals 1 over 36 for all x1, x2. By the way, that means it's again uniform. So we have a uniform distribution over all pairs. Okay. So what does that mean? That means that the entropy of x1, x2 is log of 36, which equals 5.17 bits, which equals, because of how logs behave, twice of what we got for 1 bit. I mean, for one die roll. Okay, so when we roll 2 dice and they're independent, we get twice the entropy of when we rolled 1. There's another property, another reason why people say, oh, entropy is a good metric. Okay, because when you have independent things, the entropy adds. So let me make that a general statement. That wasn't just for dice. That was for any independent random variables. And the statement is if, let's say, x1, x2, x3, as many as these as we want, if they're independent, then the entropy of all of them together is just the sum of their individual entropies. Now, when they're not independent, you have other things going on here. If things are not independent, and we go back up to this type of factorization here, we don't get a factorization when they're not independent that you just get the product. But you actually get something, you still get a factorization. You get the probability that x1 equals 3 times what we call a conditional probability, that x2 equals 6 given x1 equals 3. We're not going to deal with that for the sake of this class, but what that amounts to in terms of entropy is that in general, meaning even if they're not independent, you would have that the entropy of some sequence of random variables is less than or equal to their sum. But it's equal if they're independent. Okay, so you can't have more entropy, than if they were independent. All right. Okay, last example here. Let's do an example. We'll take the distribution we had from the lecture last time. What's this, example 3 or something? Let's say that the probability of apple, we have something that takes 4 values. And what was it? The probability that it's orange was 1/8. The probability that it was pear was 1/2. And the probability that it was banana was 1/8. Okay, so we had this probability distribution. Remember what we were doing with it? We were talking about how you would encode it with a prefix code, or how you would play 20 questions and use the least number of questions on average. Okay, that's when, and we played around with this distribution. We found that, of course, if you did it the straightforward way where you didn't care about the probabilities, and you said, well, with 2 questions, I could always find the answer here because, log of 4 is 2. All right? So, but then we said, what if we are clever and we make pair have a very short code word, we could do 1.75 bits on average. That's what we discovered. Okay. Let's calculate the entropy of this thing. So, again, the entropy of this, let's say this is x. Okay. We'll say x is this thing in here. It's the random variable. The entropy is, we do, remember, we sum the probability, 1/4 times log of 1 over that same probability, 1 over 1/4, okay? Plus, and we just go down the list like that, 1/8 log of, and I'm not going to write 1 over 1 over, we'll just put an 8, plus 1/2 log 2, plus 1/8 log 8. Okay, that's going to be the entropy. Notice something interesting here. X is not a random variable. To be a random variable, it has to actually take on numbers. This is not taking on numbers. It's a random, some random object, but its values are like apple or orange. It does not matter for calculating entropy. Entropy is really about the randomness, not about what values it takes. Okay, so we calculate this out, and what do we get? 1.75 bits. That's not a coincidence. Okay, the entropy of this distribution is 1.75 bits. And that was the average length we were able to encode it. All right, so let's explore this connection. And that's the next thing here. Let me just say this. It's okay that x does not take on, is not numeric. Okay, so now we know entropy. You have some homework problems on calculating entropy. All right. So first, for some very brief review of last time, we should remember that what did we discover? We discovered that the 20 questions game, and I'm calling it 20 questions, but really I mean the guessing game, the binary guessing game, okay, is equivalent to prefix codes. In other words, any strategy in that game could be described as a prefix code. It's a prefix because you have to know when you're done. In order to know when you're done, your sequence of answers that led to that conclusion cannot be the beginning sequence for any other conclusion, okay? Or else you wouldn't know that you're done. So it's a prefix code. We also discovered that, when related to coding, in other words, when we were talking about encoding information, we said that the uniquely decodable property implied that you have some craft inequality, which was the following. Craft inequality said that the sum of the lengths, of 2 to the negative times the length of the code word, that has to be less than or equal to 1. Okay, so to remind you what uniquely decodable meant, it meant that if you encode a sequence of observations concatenated together, that no punctuation is necessary to decode it. That's what uniquely decodable means. It means you can just encode and then encode another one and another one, put them all in a row, and you'll be able to decode. And we know that means, I mean, what we covered last time was that if it's a prefix code, it certainly satisfies craft. That's what I argued last time. But then I just asked you to believe me that any uniquely decodable code can't be better than prefix codes. Okay, I didn't prove that, but it's true. So if it's uniquely decodable, it satisfies craft inequality. This should be tight. By should be tight, I mean there's no reason to make this loose if you're trying to shorten code word lengths. You should always, if this is loose, it means you can go reduce one of your code words without ruining the prefix condition. Okay, so we should always make that tight. We also know that craft, if it's satisfied, then it means there exists a prefix code. So it's sort of a tight characterization of prefix codes. So there exists a prefix code with those lengths. So now we can simplify our discussion and just say, let's think about the craft inequality and kind of forget about prefix codes for the minute because it's equivalent, okay? And let's just worry about choosing the lengths that are constrained by craft inequality. Okay, so we can find the, I say there exists a prefix code. If you want to say, well, how do I find the prefix code? It's pretty easy. You can construct a binary tree. Assuming you have lengths, code word lengths, you can just greedily go grab leaves out of your binary tree at those lengths, and you won't have any problems. Okay, okay. So next, let's address this. Let's address an optimization problem. So here's the optimization problem. And that is, find lengths, Lx, let's find some function of x, right, that satisfies craft inequality. That means it'll be valid lengths for a prefix code. And what we want is to minimize the expected value of the length of our random variable x. Okay, now this expected length is this formula. The average over all possible outcomes, you average weighted by the probability of the length of that code word, right? So we want to minimize the average length. That's going to, of course, doing this optimization is going to depend on the distribution. Also, this, of course, has to be integer, right? For this to make sense, we need our lengths to be integers, okay? So it turns out that the way optimizing this by mathematical formula is challenging, but if we change one thing here, we can make this an easy optimization problem. So we'll relax the fact that it has to be integer lengths. So we'll let these lengths, I'm going to put a hat so that we just remember these aren't true lengths. The lengths should all be integers, but let's just say we want some numbers, L of x, that are no longer have to be integers. And otherwise, we solve the same problem. Then this is easy. Okay. It's also going to be a lower bound on the actual optimization we want to solve. Can someone say why this is a lower bound on the optimization we're trying to solve? Yes? Yes, exactly. Whenever you're doing like a minimization, if you erase constraints, you can get a lower value, right? You can't be forced to take a higher value, but you might get a lower value. So you always get lower bounds that way. Exactly. So, okay. So this will give us a lower bound. So let's solve that problem. So we can solve this using Lagrange multipliers. Now, since I don't care to teach Lagrange multipliers, I am just going to give you the answer. Although it's not hard. I mean, Lagrange multipliers are basically saying, we know we can find minimums by using calculus, but usually you do that without any constraints, right? What about when you have constraints? So you want to find a minimum, but you also have some inequality constraints. Well, you're still going to do calculus, but you're going to add in some Lagrange multiplier terms that enforce your constraints, okay? And the bottom line is the solution that you get, and really it's only takes a couple lines, but I don't think it'll help here. All right, so the solution is that the minimum is log of 1 over px. Okay, so this is the length. You would assign a length equal to the log of 1 over the probability. Does this make any sense? Well, it at least follows our intuition. Remember, your intuition is if it's a large probability, give it a shorter code word length. If it's a short probability, then maybe it'll have to have a long code word length. This is at least inversely proportional that way, right? So you're going to give your most likely sequences the shortest code word length. It also satisfies Kraft because you can just plug these in, this L hat, into Kraft inequality. Remember, Kraft inequality, you took 2 to the power of negative L of x. Once you take 2 to this negative this power, you're going to get P of x. You're going to sum over P of x, and that always gives you 1. So you meet Kraft inequality. Okay, you can plug this in, it meets Kraft. It better because we solved the optimization under that constraint, right? At least someone did. We didn't do it here. Okay. So here's the cool thing. Let's look at, suppose we use that minimum amount of, the minimization here, this L hat. They're not integers, so they're not valid lengths. But anyway, suppose we could use these. Plug them in. What's the expected value of L hat? Well, just put an expected value in front of this thing. What do you get? Yeah, I heard it. You get entropy, right? That's how we defined entropy. H of x. Boom. So immediately you get this lower bound. Entropy is a lower bound on the average number of bits you need to represent that information. Okay, now, so that means that, here's what I mean. The lower bound for L of x for any actual encoding that uses integers, it's greater than or equal to h of x. Okay, because of the integer constraints, right? Okay, but how close can we get? That's what we want to understand next. And actually, it's right in front of us. To figure out that we can get quite close to this, if you consider 1 bit close, we can get within 1 bit, at least, of the entropy. Okay? So how can we see that? Well, what if we... Okay, so I'm going to claim here the optimal code. For the optimal code, the expected length is less than the entropy of x plus 1 bit. So we have a 1-bit gap between this upper and lower bound here. Now, why do I claim that? Well, because what if we just rounded all these up? Now they're integers, right? Oops. And do they satisfy Kraft? They sure do, because before rounding, they satisfied Kraft inequality. Notice that Kraft inequality, as intuition says it should be, is inversely related with the lengths, right? This sum here. So if the lengths are bigger, this sum is smaller. So if we round up, we make this smaller, we're going to still satisfy Kraft inequality. Okay. So that's one simple thing we can do. We can just round this whole quantity up, and that gives us this bound. It's because why do we have this bound? Well, we satisfy Kraft inequality, but we added no more than 1 bit to every code word. So we couldn't have added more than 1 bit to the average code word length. Okay. Great. So now we're seeing that entropy is roughly the exact minimum, right? It's a lower bound, but within 1 bit of the actual minimum you would get from encoding. In fact, it's much more fundamental than that. Something we won't cover here, but usually you try to eke out as much efficiency as you can during compression, and sometimes that means don't just compress one observation by itself. Grab a bunch of observations together and compress them all at once. when you zip files, you grab a bunch of files, you zip them, and it becomes more efficient by doing that. Same thing here. And if you do that instead of just encoding X, like think of X as maybe one keystroke on the keyboard, some text. Instead of encoding each one separately, encode the whole sentence together. Then you find that entropy is exactly the optimal compression rate for lossless compression. This is lossless compression because we don't lose anything. We recover exactly. Okay, so let me list out now the actual encoding algorithms. I'm going to do this sort of in a historic order. We'll start with what's known as the Shannon code, and that's exactly the one we looked at above. That is just let L of x equal the rounding up of this quantity. So you see where this idea comes from. It just comes from solving the unconstrained problem and saying, okay, we want it to be close to this quantity. Let's round them all up. Okay? So we'll call that the Shannon code. And that's the one that proves the usefulness of the Shannon code is really just to very easily prove that you can get within 1 bit of entropy. All right? But we know this is usually not optimal. In fact, it's not even a viable attempt at an optimal solution because it doesn't even it doesn't even give equality in the Kraft inequality. In other words, if any rounding actually happened, if these weren't already integers, and you actually do round, then now you have some looseness in the Kraft inequality. And we know that if the Kraft inequality is loose, you can always shorten a code word. It can't possibly be optimal. Okay? So like I said, the reason why Shannon code is useful is really just to show, well, yeah, most of its use comes in just showing that you can get close to the entropy. Okay, so next we have, we'll call the Shannon-Fano code. So Fano is also an early information theorist who had some collaboration with Shannon. And this code, the only reason I mention this code, well, you'll see in a minute, it's because sort of gives us some historic context, and it's the code that many people think of. And we sort of thought of it in this class, in previous classes. It's usually the first one people think of when they try to optimize this problem. And it says sort the outcomes by probability. And then make cuts that get you as close to 50% probability as possible. All right, you remember we kind of said things along these lines when we were talking about how to address the 20 questions game. Somehow we want every cut to be as close to equally likely. Okay, so they said, all right, let's sort it and make such cuts, right? So you do something like this. Here's an example: x1, x2, x3, x4. Let's say the probabilities are 0.45, 0.2, 0.2, 0.15. Well, the first cut has to be, you have to first just cut it here to get as close to 50%, right? And that means that you're going to branch. Your first question will branch, and this will be x1 there. And then here you'll have along this direction, then you try to cut as closely as possible again. And you're going to, here it's kind of, there's some symmetry, but we would basically cut like that. And you would get x2, x3, x4, and that would be the Shannon-Fano code for that distribution. Okay, you could just assign these 0, 1, 0, 1, 0, 1. All right. Now, okay, that's not optimal, but again, it's ideas that we've discussed. What's interesting, and why this is an interesting historic footnote before we get to the solution, is that the actual solution to this problem is known as Huffman codes. Okay. Now, Huffman was a student in Fano's class. Okay, so Fano had collaborated with Shannon, and he taught a class at MIT. And Huffman was a student, and they had a choice between taking a final and doing a term paper. And the term paper had to be on this topic. It was on optimal codes for this exact problem. And Huffman was about to give up, study for the final. He had worked on it for a while, and then he figured it out. So he outdid the teacher, and basically, from what I understand, he went through just a ton of examples, like for small distributions with only a few values. He just worked out every case he could think of and went to larger distributions and then found the pattern and then could show that it was optimal. In fact, once you know it, it's not hard to show that it's optimal. So here's the idea for Huffman codes. So the difference between the right approach and the approach above is we want to design the tree from the leaves, not from the root. You can think of the Shannon-Fano codes as sort of designing from the root, trying to find the best questions at the beginning. Instead, and I'm just going to tell you the Huffman algorithm by example. Once you see the example, you'll know exactly how to do this. Let's say that our space of probability, we have a bunch of values we can take, and I'm just going to say they're x1, x2, x3, x4, x5. Okay. Hopefully this doesn't confuse you. I was using like x1, x2, x3 earlier to be like a sequence of different random variables. And here, I just mean these are the possible values it can take. Think of these as apple, orange, banana. Okay, 5 different values that the random variable can take. And we know their probabilities. So what you do is, let's say that the probabilities, P of x, is, here are the probabilities for this example, 0.25, 0.25, 0.2, 0.15, and 0.15. Okay, now you start by sorting them. Notice I have them sorted. Okay, so you do, and then what you do is, let me write them vertically here. So let's do this. So I have my things x1, x2, x3, x4, x5. I'm going to put their probabilities in the next column. P of x right here. We have 0.25, 0.25, 0.2, 0.15, and 0.15. Okay? And what you do is you first merge the least 2 likely ones. So these 2 are the least likely. When I merge them, I'm going to add their probabilities. It'll be 0.3. And I'm going to write the new list. It'll have only 4 items sorted. So notice once I get 0.3, it's bigger than 0.2. I'm going to do this all in one step. Okay, 0.15 and 0.15 become 0.3, and that becomes the most likely thing. And then and then everything else moves down. Right? That moved down. That moved down just by sorting. Okay, and that's all I do. Then I repeat. Take the next 2 least likely and add them together. I get 0.45. Again, that moves to the top. It's not always going to move to the top, right? It might stay at the bottom if the probabilities were really small. But for this example, it goes to the top. And add them again, and I get 0.55 and 0.45, and the last one's very simple. These become 1. Now I'm done. Now how does this give me a code? Well, notice this is a tree, but it's like backwards. The root's over here. The leaves are over here, and remember the leaves of our tree of our binary tree should be the outcomes, right? So what I should do is grab this root, shake it out so that they're untangled, and that's the tree I'm going to use to encode. Okay, it's kind of represented backwards. In other words, let me just arbitrarily assign 0, 1. On every branch, I'm going to do 0, 1 like this. Okay? And then what I can do is I can write down what the code words are for each of these by saying, by looking along the branch of the tree that gets there. So this follows a certain course like this. X1 follows these paths. They're not labeled. And it gets here, and it's got a 1 and a 0. So we start at the root. We get 0, 1. That's the path to get to X1. 0, 1. Okay, and to get to X2, what did we do? Following it back, we went 1, nothing, and then 0, right? All right, so 1, 0. You see what I'm doing here? I have to trace this way to figure out which way to go. So it's here. It's got a 1 and a 1. And of course, I read it out in reverse order. Okay, here this has a 0, 0, 0. And lastly, we have a 1, 0, 0 in reverse order, 0, 0, 1. Okay, you can check that is a prefix code. In fact, that's the optimal prefix code for this distribution. All right. Now, really all we care about is the lengths. Okay, let me make one argument why the Huffman code is in fact, as I make this summary, why Huffman codes are actually optimal. Well, first of all, let's look at what is the length, L of x. Well, it's 2, 2, 2, 3, 3. I can go reassign. The actual code words themselves are not crucial. I mean, it's not unique. I can make different code words that still prefix code. What is unique is the lengths that I needed to be optimal. Okay, I needed to make these 3 have length 2 and these 2 have length 3. All right. If you want to argue for yourself, I'll leave it mostly as an exercise, why this is optimal. You really just need to know that the longest 2 code words, first of all, if you knew the lengths, if you were given a set of lengths that satisfy craft and you said, using these lengths, design the optimal encoding for a given distribution, then it would be easy. All you would do is you know that you have to give the least likely things the longest lengths and the most likely things the shortest length. You just sort your probabilities and you'd assign them out. You'd give the most likely ones to the shortest lengths. Okay? So to prove that Huffman's optimal, you really just need to know that the longest length, there's always going to be 2 longest lengths, and they'll be the 2 least likely outcomes. All right? I mean, sorry, the longest length will not be unique. There will be at least 2 outcomes at the longest length. That's easy to argue. No binary tree that's efficient will ever have a single longest branch here. And once you have that argument, then you say, okay, then I could have always, without loss of generality, assumed, since these are the same length, that their codes are exactly the same up to the last bit. And so I could just merge those 2 least likely things together and resolve the problem. Okay. So in words, very quickly, again, leaving most of the thinking to you, you can convince yourself that Huffman codes are optimal. Okay, so the summary for this part, for today's lecture, is that, and for coding in general, for lossless compression and for Huffman codes, first of all, we had that the craft inequality implies that the expected length is greater than or equal to the entropy. Okay? So that's going to be true for any prefix code. We achieve this if, for example, if Lx was not required to be an integer. And we would set the lengths to be the inverse, the log of the inverse of the probability. All right. Now, if it happens that these logs of the inverses are integers already, then of course we achieve entropy exactly. Okay, so we could get lucky and they could just be integers already. In our example with orange, apple, pear, banana, we were lucky. We could achieve entropy exactly because log of the inverses were integers. Okay. We also saw that the Shannon code gets close, right? So if we use a subscript S for the Shannon code, and that was just a rounding up of these, and that the expected length of this guy is less than the entropy plus 1. All right? And then the Huffman codes are optimal is the last thing. Let me show you just an example to just remember why Shannon codes are, in fact, not actually optimal. They don't meet Kraft. And we can see that by just taking pretty much any example. Let's say it takes 4 values. Px1 so there's 1/6, 1/3, 1/6, and 1/3. Okay, so the Shannon code for this says the length of this one should be round up log 2 of 6, and that is going to be 3, right? Okay, and this one here is going to be 2. This one here is going to be length 3. This one here is going to be length 2. Okay. Now, if I actually want a code, I'm guaranteed that these lengths satisfy Kraft, so I should be able to do a code. Let me just do it in a greedy way. I'm going to say I want a length 3 code word. So 1, 2, 3. I'm going to do. I'm going to put x1 here. Now I want a length 2 code word. So I'm going to take the closest spot. I can't take this. I can take this and make that x2. Okay, now I want a length 3 code word. I can take this guy and make it x3. And I want a length 2 code word again, x4. There is a binary tree. It terminates, and that this is the code, the Shannon code. But obviously, we're not being efficient. We wasted something here, right? I mean, why would we not shorten that? Why would we not just shorten that code word? Okay, and that's what it means to not satisfy Kraft. So yeah, I mean, it's an okay code, but it's certainly not optimal. You can just improve it. All right, and yeah, the final thing is that the Huffman codes are actually optimal.